So we continue our conversation about principles or fundamentals of optimization in the context of machine learning. And we are calling the function that we'd like to optimize f. So f is assumed to be a function of w, the weights. And what we're expressing here at the top is that the objective function or the error function or the cost function, we don't know what that is, at least right now explicitly, but with this in mind, w is an independent variable, and therefore f, when evaluated at w, is going to be considered a dependent variable. So f is a dependent variable that takes in as an input the independent variable w, which are considered the weights. So we're going to make a reflection here, something to think about as far as when there are variations in w. And so we want to picture f of w in the vertical axis, and then w is denoted here on the horizontal axis. But these are one-dimensional independent variables. So we are going to think of what happens if there are variations. So right now we're assuming w has a specific value evaluated at 4, and then f evaluated at that value is almost 10, right? So it's this is with the idea of motivating a few things. What we want to motivate next is what happens if we vary the independent variable, how that influences or changes the error function or the cost function. So in this particular case, we really would like for the error function, we really would like to consider how f of w goes down to 0, or how f, the error function, approaches 0. That's what I'm writing here on the lower left corner. How, because when the error goes to 0, that's the ideal scenario to be in. So w is one-dimensional, and how would the error function change when w changes? That's what we would like to address here. So we consider another value of w. So remember, initially w is evaluated at 4, and what happens when we go from this value of 4 into a variation into a value of 6? What happens when w is evaluated at 6? What happens to the cost function, the objective function? So in this case, this gives us a value that's almost 22, right? So what we're considering at this illustration by having a sense of change, and therefore there is an arrow here that's kind of illustrating how one value of a function is changing, but in a vertical sense, it's almost as if that value is now changing upward, right? So it's changing into a value that's bigger than the previous value of the function at the previous value of the weight. So what we're assessing is how the function f of w, the error function, changes relative to variations in the independent variable w, the weights. So for example, what if we change w from w equals 4 to w equals 2? So the value obtained, and again, we don't know what the specific form of the function, the cost function or objective function, we don't know what that is. We're simply motivating this as if we had partial information of evaluations of this error function at specific weight values. Okay, and so in doing that, we would be moving from 4 in the horizontal sense, from 4 into 2. So that's like as w decreases, then what happens to the function f of w? So what happens to that function is that in the vertical sense, that function goes down. So where we're heading with this is like change in W versus change in f of W. Okay, and so this notion of considering this ratio of the change in the independent variable versus the change in the dependent variable, there you should be thinking about something that looks like x1 minus x0 divided by y1 minus y0, right? So this is this ratio that is known as slope, and that slope of a line is going to be key for addressing rate of change. Okay, and so in particular, what we call derivatives are instantaneous rate of change in a limit, in a very specific limit. But that's where this conversation is going. So there is a term here, gradient. So gradient is basically the mathematical term, the technical term for rate of change, specifically in higher dimensions. And the gradient has direction. So the gradient is going to be associated with a vector that describes the direction. And so now in this illustration we see here on the screen, so we see that there is a curve. So this curve is f of W, right? And here is W, the independent variable on the horizontal axis, right? And so what we're seeing here is how f of W basically has the shape of a parabola. So here, this is being motivated by thinking that f of W is approximately something that could have a parameter there and then maybe W squared or something like that, right? But even without knowing a specific form of f of W, at least right now we see a shape. And what we're trying to address is the rate of change for this function f of W, which is called the cost function. So this is, remember, the error, the cost, is what compares the observed versus the predicted, right? So that's what is the underlying function that is being minimized. And we'd like to have machine learning models that attain the smallest possible discrepancy between observations and predictions, and that have the values, the optimal values of weights that would give that minimum error, which is that translation of observations versus predictions. So all of this is basically orchestrating algorithms to have a way of finding these optimizers of this optimum of weights that basically are in a minimum for the error function. So on the next following 4 slides, we are addressing a specific form of the error function. We're assuming it's quadratic and W, and it has a factor there of 0.6. This is for purposes of illustration. So normally for one variable we write something like f prime of W. Here we're using the notation of instead of writing f prime of W, we're writing something like this triangle of W, which is actually called the symbol for gradient. So what you're seeing on the next few slides is basically change in W. So you could think of like something as like W 0 minus W1, or maybe the other way around, divided by change in F, right? Evaluated the same values of W0 and W1. So the change in W occurs on the horizontal sense, because this is W and this here is F of W. So you're going to see some of these errors, which are really illustrating changing the independent variable either to the left or right, because that variable only lives on this one-dimensional space, which is the horizontal axis. And then you would see this symbol of gradient of f at specific valuations. So basically what we want to keep in mind here is that what we want to illustrate is that the gradient of f is going to be analogous to a slope, and it would be a slope of a line, but specifically the slope of a tangent line at specific points, at specific values of the independent variable. For example, when we consider the tangent at 2, then given that f is 0.6 w squared, the gradient of f would be basically the derivative of this expression, and that gives 2 times 0.6 times w, and then when you evaluate that at a specific value of w, that's what gives in this case the 2.4. The important thing is that here this 2.4 is positive, and that positive is going to be basically that sign, the fact that that is positive, that's going to be consistent with having a line with positive slope that is tangent at w equals 2. Now, so if we evaluate at another value of w, which in this case would be 4, we can see that the gradient at 2 has a value of 2.4 positive, and then the gradient evaluated at 4, so that would be evaluating, basically considering a tangent line right at this point, that would also give a positive value, which is associated with the slope of a line, which is actually quite steeper than the previous line. So if you could imagine, like my annotation here is not super great, but a tangent line at w equals 4 would have a slope. This is a line that would have a slope of approximately 4.8. So a little steeper slope than the previous one, right? So the gradient may be evaluated at specific values of the weights. And in this case, with 2 evaluations, we're getting 2 positive values. It may be negative, which is what happens here when the gradient is evaluated at -3. So then you can imagine a tangent line there with a negative. So in this case, the slope is a negative slope, right? And that negative value is also steep in a negative sense. So the important thing is that we can associate these values of slope, which are there. A slope may be 0, or it may be positive, or it may be negative. If it is very positive, it has a local increasing behavior of the function, in this case the function f. If it is very negative, it has a local decreasing behavior. So when we have to make decisions as to which values of w to consider and how to consider variability in w, we would like to guide that decision by inducing the most reduction by using, hopefully finding negative slopes that are going to bring this idea of decreasing the cost function the most.